Hello, one and all, and welcome back to another exciting lesson of AP Statistics. Today, we will start Chapter 10 in our book, and Chapter 10 is kind of the cornerstone for inference. It's really, really important because Chapters 10, 11, 12, 13, and 14 are all about what we call inference. So you really need to focus on Chapter 10, make sure you kind of understand what inference is all about. And that way, when we try to do inference on different distributions, it'll be like, oh, I already know how to do the inference thing. This is just a new distribution. Versus if you crash and burn in Chapter 10 and you don't learn inference, well, it's not going to go away. You're going to continue to crash and burn. So put in the time right now, and let's try to get it figured out the first time around. Okay, so when doing inference, there's two things, right? One would be making confidence intervals, and two would be performing significance tests. Today, we're going to be doing confidence intervals, okay? All right, so a confidence interval is just an interval estimator of a parameter. So up till now, we've said, here's X bar. Well, X bar is a number. It is a point, a single number, a single point. So it is a point estimator for mu. Okay. P hat, that's a point estimator for P, so on and so forth. Well, a confidence interval kind of gives a little more information. You see, it's going to give a lower bound and an upper bound and say, hey, within this interval is where we think the parameter is, okay? Now, we're going to give some, it's called a confidence interval. We're going to have to give some confidence level. Most commonly, we'll say we're 95% confident that our parameter is between this and this. Sometimes we'll do 90%, sometimes we'll do 99%. I mean, technically, we could do any percent we want, but those are the most common, 90, 95, 99, with 95 being the most confident, or the most common confidence level. And it should make sense because knowing what you know about the normal distribution, right? Empirical rule, if you just go 2 standard deviations in either direction, you're gonna, cover about 95% of the data. So back in the day when we didn't have a whole lot of technology at our disposal, we would just say, okay, add and subtract 2 standard deviations, there's our 95% confidence interval, roughly. All right, so here we go, the confidence interval. 2 parts, as I already mentioned. First, there's an interval, right? So it takes our estimator, our point estimator, and then we just add and subtract our margin of error. So if we want 95%, our margin of error is roughly 2 standard deviations. As I already mentioned, we also need a confidence level. Again, 95% would be roughly 2 standard deviations, okay? Typically, we do 90, 95, 99, or some other 90-something. And a capital C just stands for the confidence level. That's like abbreviation. So if we say C equals 0.95, you go, okay, 95% confidence level. All right. Sometimes people will say, why stop there, right? Why only do a 95% confidence? Why don't we go to 100%? Well, to get 100% confidence, your margin of error would have to be infinity. And now it's pretty useless to say, I'm 100% confident that the true mean is between negative infinity and positive infinity, right? You haven't said anything of any value there. So that's why we can't go to 100% confidence. All right, so today we're going to be doing confidence intervals for population means. So that's the distribution we're going to be looking at. As I mentioned, in future units, we'll look at confidence intervals for, say, proportions, right? So on and so forth. So in each unit, we'll be doing different distributions, but we'll be doing the same procedures, inference. And again, in today's lesson, it will be confidence intervals. All right, so when can you safely construct a confidence interval? Okay, if I'm looking at the distribution of means, my sampling distribution, right, of sample means, the data needs to be collected in an unbiased way. So in other words, we need an SRS. Okay. We're going to be today looking at the sampling distribution of X bar. And we know that that will be approximately normal thanks to the central limit theorem as long as n is large enough. And again, we'll talk about what's large enough later on. For now, just say, oh yeah, n's 50, that's large enough, should be approximately normal. We'll talk about putting numbers on that in a future lesson. We don't want to overwhelm you all, at once, because again, this is a big topic without that included. This we've already mentioned. The population needs to be at least 10 times the size of the sample. That's in order to safely use your standard deviation formula, right? Sigma over square root of n. And again, I talked about the why. If my sample size becomes too large, then from one sample to the next, I won't see any variation, or I'll see very little variation. So that would invalidate that piece of the calculation, because we would be assuming that we would be getting that variation based on our formula, but in reality, we wouldn't be getting it because our sample size is too large proportionally to the population size. All right, so because we're saying the sampling distribution of X bar will be normal, that means we can use z-scores. Okay, now this z is called, it's a z with a star on it, so z star. That is our critical value for z, right? It's the value for z that's going to capture whatever amount of the distribution we're stating that we're capturing. So 95% z star, it's approximately 2 standard deviations by empirical rule, but we're going to be a little more accurate than that. Okay, so I think I have that on the very next slide. Yes. So let's practice real quick. Let's say we want to do an 80% confidence interval, right? How many standard deviations on a normal curve would I have to go in order to capture 80% of the data? So, right, we want this to be 0.8, which means we need 10% there and corresponding 10% over there. So using table A, I could look up either 0.1 in the body of the table and find out the z-score, the number of standard deviations, or I could look up 0.9 in the body of the table and figure out how many standard deviations, right? So let's do that real quick. Table A. Let's say I look up the 0.1. We're right in here, right? Here is something very close to 0.1, a little bit above, and then that's a little bit below. So we're somewhere between negative 1.28 and negative 1.29 standard deviations, okay? Remember, we can use inverse normal on our calculator if we want to be more accurate. I think we just do 0.1. Yep, so there it is, more accurate. Now, there's another one on the other side, right? If I look up 0.9, notice I get the same value. It's just positive now because the normal curve's perfectly symmetrical. So rather than giving both, we've decided we just always report the upper critical value. So in other words, we just always give the positive. So go ahead and look up the one on the left if you want. If you think that's easier, that's fine. Just make sure when it's all said and done, if they say what's z star, you'll give the positive one. That's just what we do, okay? And there you go. That's how you can find any z star that you want. Pretty simple. All right, now, as I mentioned, there's certain common confidence levels. So here's our most common confidence levels, 90, 95, and 99. And again, please understand that your tail area, right, it's always, a single tail is always half of 1 minus the confidence. right? Because, as I just drew here, right, the confidence here is 80%. So a single tail is 10%, right? Half of the complement, because there's two tails on a confidence interval. We're getting the center section. Okay, that's a common mistake. Now, here they are, rounded out to 3 decimal places. If you want more decimal places, guess what? Go for your calculator, right? So let's do the 90% on my calculator. So in this case, I would want that to be 0.95. So there we go. There's the Z star right there, but to more decimal accuracy from your calculator. Now, again, you could look that up in table A, right? So I could, as I showed you earlier, look through here. Let's find 0.95 in my table, and there it is between those two values. Okay. Furthermore, I'll show you this. We're not really to this table yet, but this is where I find my Z stars. I mean, obviously, again, the calculator's fast, but if you keep looking through this, eventually we get to the end of table B. And if you look at the bottom of table B, you'll see confidence level C. And here's the 80%, 90%, 95, 96, 98, 99. So there are those values, also quick and easy. So if you don't have your calculator and you don't want to dig through table A and realizing that table A only has 2 decimal places of accuracy, and then you're always landing between 2 of those, right? Here's where I can go to get 3 places of decimal accuracy quick and easy. Okay, we'll use this table more later. This is the t-distribution, which is something we're going to do this semester. Yay, fun. Okay. All right, so as we already mentioned, the Z star, that's known as the critical value, okay? And that's the number of standard deviations you have to go in order to meet the confidence level that's required, right? To capture the right amount of data from the distribution. Okay, and as I already mentioned, we report the upper value, the positive one, so some people will call it the upper P critical value. And you can think about it as the confidence level plus half of the complement of the confidence level, right? Because that's what you would enter in your calculator, right? Or you can think about it as, well, how much is above it, which would be, again, half of the complement of your confidence level, because there's 2 tails. Okay, but that's why you will see, I guess I'll go there. You will see sometimes instead of Z star, you'll see this Z and then subscript alpha over 2. Because the complement of the confidence, so 1 minus your confidence, that is equal to your alpha. We'll talk more about that later. But this is another notation instead of Z star. I kind of like this notation better because it, again, kind of reminds you that, right, here's your confidence. Well, over here is 1 minus your confidence divided by 2, and over here is 1 minus your confidence divided by 2. So if 1 minus your confidence is, we're going to define that as alpha, then this is alpha over 2. That's alpha over 2. So when we say Z alpha over 2, it's kind of reminding us, oh yeah, remember, right, there's 2 tails. I don't think our book uses that notation, but a lot of books do. So I think our book uses the Z star. All right, so here's how we do it. It's really simple, right? We calculate our statistic, and in today's lesson, we're talking about sample means, so that's X bar. And then we're gonna add and subtract a certain number of standard deviations to capture whatever confidence that we were trying to get, okay? So again, roughly 2 standard deviations will get you 95%. But we figured out it's actually 1.96, right? And of course, our standard deviation, we've learned, is going to be based on our sample size. So it's the standard deviation for a single individual divided by the square root of our sample size. Okay. And again, Z star, that's the upper critical value, the Z alpha over 2 critical value from the standard normal distribution. Also realize the way we're going to control the width of our interval is by our sample size. It's that same relationship. If you quadruple your sample size, you will cut your standard deviation in half. All right, so the margin of error. This piece right here, that's the margin of error. So to create a confidence interval, it's your statistic plus or minus your margin of error. That might actually be on our formula sheet too. Let me take a quick peek and see if I can find that. Yep, sure it is. There it is, sure. As I said, confidence interval, it's your statistic plus or minus your critical value multiplied by the standard error statistic, okay? So right there is your critical value, Z star. Right there, that's the standard error of your statistic. Or in other words, your statistic standard deviation, okay? But the whole thing, critical value times the standard error gives you the margin of error. All right. So confidence intervals, that's what the whole lesson's about. Well, how do these confidence levels behave? The goal obviously would be we want the highest possible confidence. It doesn't do me any good to say I'm 0% confident that it's blah, blah, blah. Who cares, right? Doesn't really do me much good to say I'm 20% confident, right? We need to have a confidence level that we go, okay, there's a pretty good chance it's in there. But the problem is, as we increase our confidence, right, we have to make a wider and wider interval, right? That's why I was saying 100% confidence. Well, now my interval's negative infinity to positive infinity. That's also no good, right? So the goal is to get as high a confidence as we can, but a low enough margin of error that we've actually kind of pinned things down, right? That it actually is useful. Okay, so again, high confidence, that means we have a high chance that we've captured the true parameter. And a low margin of error, that means we've pinned down its actual location. So like here's a visual, what we're talking about, right? That's the goal there. Okay. All right, so let's talk about the margin of error, which is, again, our Z star or Z alpha over 2 multiplied by our standard error of whatever distribution we're working with. In this case, sampling distribution of X bar. Okay, we said we want to have a narrow confidence interval. So that's all dictated by the magnitude of the margin of error, right? So we want that to be as small as possible. So how do I make it smaller? Well, there's 3 pieces of the puzzle, right? Well, I could change my critical value, but if I make my critical value smaller, I've sacrificed confidence. And again, it's no good to say I'm 20% confident. So typically, can't really change that. It's going to probably be dictated by the problem, or in the real world, if you're conducting research, whoever pays you will say, I need at least 95% confidence, or at least whatever percent confidence. And you may recall during our last election cycle, before the actual votes were in, they would constantly say, oh, so-and-so is polling at whatever, plus or minus 3% with 95% confidence, right? They would say these things. Well, that's what they were doing. So, CBS or whoever would say, hey, I need a poll, but I want at least 95% confidence. So your hands are tied. Can't control your critical value. All right, next thing that controls the margin of error is, of course, sigma. Sigma, however, is a parameter. So guess what? Can't change a parameter. It's fixed. So that really only leaves one possibility, your sample size. All right, so that's how you're going to control the margin of error, is by increasing your sample to decrease the margin of error and therefore get a more narrow interval. And again, we've mentioned this before. Since it's the square root of n in the denominator, if you want to cut the margin of error in half, you will have to quadruple your sample size. Okay, last piece of the puzzle. Oftentimes, companies are hired to go out and get data and do a confidence interval. before they actually have any data collected, right? That's typical. So what they'll do is say, oh, I need to get, whatever margin of error. I have whatever confidence level requirement. Here's my standard deviation for one individual, and then they'll solve this to figure out, oh, okay, well, I need a sample of at least 1,000 or 1,500 or 900 or whatever the sample size would be. So that's how they figure out how big of a sample to take before they've actually collected any data. All right. This is going to, again, be a big topic. We're going to do it over and over and over again. So here's some cautions, some common mistakes, some things to avoid, okay? Number one, in order to do this particular confidence interval and pretty much any confidence interval, we need good data. The data has to be unbiased, okay? And our typical way of saying we have good data is, did it come from an SRS, right? Because it has to be, the whole calculation is based on random chance. So the data should be collected by SRS, right? Simple random sample. The formula technically doesn't work for anything more complex than an SRS technically, but if you have good data from some other, method, maybe a stratified or something, we'll typically bend the rules and say, okay, go ahead. But you do need good unbiased data. And again, stressing that. If you have biased data, if you have bad data, there's no way to correct it. It's over, it's done. Your interval will be off the mark because your data was off the mark and there's no fixing that. Okay, you need to be careful about outliers, especially if you have a smallish sample size, right? Because if you have a small sample size and you get an outlier in there, it's really gonna move your mean a long distance, and that can really pull your confidence interval either up or down, right? Depending on which side that outlier landed. So be careful of outliers. Okay. We're going to be doing a Z star, meaning a normal. We're using a normal distribution, which means we need normality. So be careful, especially if you have a small sample size, to look, is the data appearing to be normal or not? The good news is, central limit theorem says for this particular distribution, as long as n is large enough, we will have approximate normality. But again, we haven't really discussed, well, what's large enough. So just always at this point, take a peek at a graph of your data, and does it look fairly normal or does it look extremely non-normal? Okay, and then here's the last problem here. We're pretending to know that parameter right there. If you think about it, how could we know that parameter and not know the population mean? Right? It's pretty nonsensical, right? To get that parameter, the population mean is in that calculation. So right now we're kind of in make-believe land. We're pretending to know something that we wouldn't know. In a future chapter, we'll see how to handle it without that, make-believe parameter, okay? But for now, we'll just pretend we know that, just to kind of learn the process and understand how things work, and then we'll kind of build on that and move from there. All right, so let's practice. Let's say I have a data set, it came from an SRS. The population has a standard deviation of 2. My sample size was 49, and my sample mean was 20. Let's find a 99% confidence interval for the true population mean. Okay. So a big part of this inference piece is that you validate your calculation. So you need to mention why your calculation is okay, and then you can do your calculation, right? So first thing we have to say is the data came from an SRS, which that is something that's a requirement of this calculation. Okay, so the data came from an SRS, okay? Now, another requirement of this calculation is that our population is at least 10 times the size of the sample. it doesn't say what the population we're dealing with is. So we're going to have to assume, okay, assume the population is at least 490 in order to safely use the standard deviation formula. Okay, in this case, that's sigma over square root of n. Okay. All right, and then last piece of the puzzle, we need to have approximate normality. Okay, I'm going to just invoke at this point. I can't graph this and look at it, right? Because they didn't give me the raw data. They just gave me the statistics. So since I can't graph it and look at it, I'm just going to invoke central limit theorem because I'm talking about sample means, and n of 49 is actually large enough. But again, we'll talk about those cutoffs later. So I'll just say the central limit theorem. Assures approximate normality of the sampling distribution of X bar when n is sufficiently large or large Okay, so we've now validated our calculation. We've obviously had to make an assumption about the 490, but that's okay. The person reading your work would know, hopefully, what this population is and would say, okay, yeah, it is 490, right? Otherwise, what good does it say? Oh, yeah, the confidence interval is this to this if you don't even know what population you're talking about. Okay, so let's do our calculation, right? So our calculation is we're going to take our statistic and we're going to add or subtract our margin of error. Okay, well, our statistic is 20. We need a 99% critical value, so you can use table A, you can use your calculator, or you can use the t-distribution back page. Again, I just flip to the t-distribution back page typically, so there we are, 99%. Okay, sigma is 2, and sample size is 49. And there you go. We work this out. We'll have a confidence interval. Okay, so working that out, we get this. Here's my interval. Okay, 19.26 to 20.74. Now, part of formal inference is at the beginning, we validate our calculation. We do our calculation in the middle. Then at the end, we need to write a statement that states the interval and the level of confidence. So we would say I'm 99% confident that the true mean of blank, right, if we had context, the true mean height of whatever or weight of whatever it is, the true mean of whatever it is between, in this case, 19.26 and 20.74. And there you go. You just did your first confidence interval. Hopefully it's not that bad, right? The calculation is pretty simple. Hopefully it makes sense. It is a little bit tedious because we're doing formal inference. So validate the calculation, do the calculation, and then give me a statement stating both the confidence level and the interval. Okay? And you should have this in context whenever there is context. Okay, so units. All right, let's try another one. All right, let's say we have a population with a standard deviation of 1. How large of a sample would I need to take so that I get a margin of error less than 0.1 with a 99% confidence? So this time, we're not actually calculating the interval. We're calculating, well, how much data would I need in order to make this interval that they want. Okay. So notice a lot of students see this and they freak out. Mr. Crow, there's no X bar. How do I do the problem? Of course there's no X bar. No data has been collected yet, right? We're not actually doing the interval. We're asking how large of a sample do I need? Okay. So we're only using the margin of error piece of the puzzle, right? There's the margin of error. And we're saying it needs to be less than, in this case, 1/10. Okay, well, they gave me sigma and 99% confidence, so I can look that up, I can plug that in, and then I just solve for n, right? So 99% confidence, again, 2.576. Sigma is 1. And now it's just simple algebra. Okay, solve for n. Solving for n, we get this right here. Okay, 663 point whatever. Now remember, this is a sample size, so n must be a whole number. I cannot have 663.6 people or items in my sample, right? It has to be a whole number. But again, you'll always end up with an inequality, right? When you solve this, you end up with n is greater than something. So that means when I interpret this, that my sample size must be at least 664, right? So that's how we're going to change from the greater than over to greater than or equal to, right? We always just go up to whatever the next whole number is. Again, please answer this in a complete sentence. Okay, so to achieve this margin of error with a 99% confidence, we would need to choose a sample size of at least 664. Notice, by the way, I didn't have to validate this calculation because I haven't actually collected the data yet. I don't have to talk about SRS. There has been no data collected yet. Right now, I'm just figuring out what size sample is needed. Okay. All right. So there you go. Day one of confidence intervals. We're going to spend many days doing confidence intervals on different distributions, but this is the key. So make sure you understand this. That way, when we do it again on the next type of distribution in a future unit, it'll be a breeze. The only thing that'll be different, we'll be using something other than z, right? We'll be using a different value for our standard deviation, right? But those are the only things that'll change. All the logic and reasoning and steps will be basically the same. Okay, thanks for tuning in.